So hi everybody, today is Monday, May 10th, 2021. This is Bill Bittner from the ZVM Education Club. And today we have the esteemed Alan Altmark here to talk to us about the virtual switch. This is a two-part session. So with that, I'll turn it over to Alan.
Thank you, Bill. Good morning, good afternoon to everybody. Pleasure to talk to you all again. I do enjoy being able to share information with you. So developed a pair of presentations, and it turns out that it does take a couple of hours to get through all this, which is why it's split into part one and part two. And part of the problem is that when I go into client shop, or in fact, I'm at an event, and I ask for a show of hands, how many of you in the room are networking people? And a couple of hands will go up. And of course, the correct answer is all hands have to go up. Because if you're going to manage a ZVM system, there's an awful lot of stuff you have to know, right? Make you understand disaster recovery, backup, accounting, security, networking. So it's all part and parcel of your day job if you're going to be a ZVM systems programmer. Occasionally, I will come across clients which might have a couple of people managing their ZVM systems, and they can have really good help from the folks around them, aren't really part of the ZVM team, but they'll have good help from their networking people. And these guys are really, really successful at deploying virtual networking. So part of the purpose of this is to be able to let you have a common language to be able to share when talking to clients, sometimes you get on a call and you're talking not to the system programmer, they get somebody on a call and it turns out it's their networking person. And you really have to have a common language to speak to them. And so that's what I want to try to do here is be able to, everybody understands what we're talking about when we're talking about virtual switches. All right. First of all, before I talk about the switch, I have to talk about the context in which it lives. And this picture hasn't changed in 25 years. This is what often, regardless of whether we're talking about discrete physical servers, whether we're talking about virtual servers, whether you're talking about containerized applications, it doesn't really matter, okay? But the point is that this is what, when we deploy from a networking point of view, this is kind of what everything looks like. And the thing I want to kind of get here is the idea that there are zones in a network. And zones, it's a little bit of a vague term, but what it really means is that it's a part of the network where there's separation from the other parts of the network. Now in here, I'm showing an internet zone, a web zone, application zone, and the database zone. And so we refer to this as a three-tier application. Because what happens is that, you go into, you're trying to reach an application, right? But the first thing that happens is you get one of those sign-on, right? That actually happens in the web zone. So actually, this is the set of servers that are kind of, your authentications are kicked back to it. You might reach the application, first thing, but you're going to get kicked back to the web zone so that you can do authentications, for example, and we find out who you are. And then from there, if we're successful there, then we'll let you into the app zone. And then the apps reach over, they have to go through another zone into the data zone. And I show these red, green, blue, but there can be, pink, yellow, light green, dark blue, magenta, cyan. So we have lots of different colors we can use for these things because there are lots of different zones in a shop. And in particular, what you should run across is that there's a production set of these, and then there's a test set, okay? So I might have light red for test, light green, light blue, because I need to simulate these zones even in a test environment. And so the zones are separated by firewalls, some sort of filtering mechanism that's not on the host itself, because we do have host-based firewalls, but these are the utility firewalls that sit in the network devices. That's what really creates the zones, because for one thing, I can push a button and the gates come down, right? So code red, and then I push a button and all of my firewalls close their doors, right? So I could, if there's an ongoing attack, if I'm detecting massive data breach, I can shut the whole thing down by just, the number of firewalls is far fewer than the number of servers. So that's how I would, how I can handle that. All right, so what happens then is we want to implement these on Z. And how are we going to do that? We're going to do that with the virtual switch. Because out in the physical world, those firewalls, they're sitting in switches, and we're going to have, in this configuration, what you're going to see is an outboard firewall. Firewalls, those appliance firewalls, they're actually resident inside the physical switches, and they don't live on ZVM. One of the things that for a while, about 15 years ago, there were commercial firewalls available for Z. They ran on Linux. They were utility firewalls, and it was very nice, except it was too expensive to operate. And it wasn't Cisco, and it wasn't the name brand that people like to have, because when they deploy firewalls, they want to have the same brand throughout the enterprise, right? Because that way they have a common dashboard, a common management interface, a common set of training. So the firewall business on CVM, on Z, actually disappeared. So the host-based firewalls are still there. Those are the defensive firewalls that sit on the servers themselves. Those are there. But these utility firewalls that create the zones, they're out in the physical network, right? And that's okay. I'm not going to argue with somebody about that. So yes, it's true that once I enter this network, I'm coming in from the internet, let's say, I bounce off the firewall, I go through my interior firewall, those outside firewalls, and then I have my interior firewalls. And that lets me get into the web servers. I want to get from web to app, I leave the box and I come back in again. Want to get from app to database, I leave the box and come back in again. And I said, well, why can't I do this? I have all sorts of things that let me, I can use hypersockets, I can use PCI cards and Rocky cards. I can do this, very nicely. And I go, yeah, nobody cares. Okay, network people don't care about our cool technology. What they want is to make sure that the firewalls are doing their job. They're responsible for data security. And if things are going around the firewalls, they can't see it. They can't see it. They can't control it. Okay? They can't monitor it, first of all. They can't even report on it. So I tend to find that all of our cool onboard, inboard data connections typically don't work very well in the field. Not from a technology point of view. They work great from a technology point of view, but it's really hard to get them deployed. It takes a lot of trust and takes a lot of time to let the clients move on. Right, so we've got these virtual switches, but before I talk about a virtual switch, I need to talk about a physical switch, because it doesn't help to virtualize something that you don't know what it is. And I go into a client, talk to the ZVM system programmer, and they're aware of the existence of these things, but they don't know what they do, really. So it is the device that manages the network. First of all, it's not the thing you typically have at home. We have things at home we call switches, but they're not really, sort of, but you don't pay enough for it at home to really have a switch. But what I'm able to do with these is I have a management interface I can use, a command line interface, a browser interface. Most Cisco switches, you still SSH into them and you issue commands. But you can turn ports on and off. Most sites, I know IBM has a network policy that says if a port is not in use, it's turned off. Nobody can just wander up to a blank port, plug into it, and hook into the network. Not going to happen. Okay. So the network people turn these things off, but they don't have to go physically unplug anything, right? So they administratively turn it on and off. They can assign the attributes of a port. You'll find in my pictures, I use colors to represent subnetworks or LAN segments. A LAN segment and a subnet, those two things are synonymous. They mean the same thing. Every LAN segment is its own subnet, and every subnet will be in its own LAN segment. That's not a physical requirement. I can actually do something called multi-netting, where I run multiple LAN segments on the same physical LAN segment. But there's a ninth circle of hell that's reserved for network administrators to do those sorts of things, and it's a good way to lose your job. So because it's not secure in that respect. So just because you can do a thing doesn't mean you should do a thing. So what we do is we say a LAN segment is a subnet. There's a mechanism on here to be able to set up sniffer ports so that I can watch the traffic, because in a switch, you can only see the traffic that's meant for you. If it's not meant for you, you never see it on the wire. It doesn't come to you. That's part of the intelligence aspect of a switch. And it turns out that you look on there and there's little numbers on there. So that's when I'm managing it. I say, well, do this to port number 5, okay, or port number 7. And I set the attributes on a port basis. Okay, now we have a concept of, well, of course, the world does not consist of more of just one switch. I have 2. Well, in particular, what happens when I fill up one? You don't throw it away and buy a new one. You might spend $10,000 on these things, right? So you're not going to throw them away. What you do is you expand them, and you expand them by doing what we trunk them together. That's the term of art we use. We trunk switches together. And when we do that, we create what's called a bridge. The ports that are providing that are called trunk ports, and they are configured to carry information about multiple LAN segments on one cable. Now, from the point of view of somebody who's plugged into, say, one of the green ports, all they see is green traffic. They don't even know it's green, all right? You just plug into the network, I have an IP address. I couldn't care less how many LAN segments are involved. As an end user, I don't care. I can't do anything about it if I do care, and sometimes ignorance is bliss. And people can move me around and I still don't care. All right. So those switch ports, they don't actually carry, if I look at the traffic flowing on them, on the colored ones, 2, 3, 4, 5, and 6, I don't see any information in there. There's no data in an Ethernet frame that tells me, is it 2, 3, 4, 5, or 6? But on a trunk port, there is. Trunk ports carry what are called tags. This is where VLANs come in. So virtual LANs. Virtual LANs are not something that ZVM invented. Okay, virtual LANs have existed in the IEEE. So it's a standard, is a way to be able to, how do you change the format of an Ethernet frame to carry data that says, what LAN segment am I? Because the green ones on switch number 1 on the top switch want to connect to the green ports on the other switch, but it doesn't know what ports they are. It doesn't need to know physically what ports are they. Just as traffic needs, for example, somebody plugged into one of the green ports, they issue a broadcast. Well, it only goes to the green ones on the top switch, but it also goes to the green ones on the bottom switch. So that broadcast exited the trunk port, but it was tagged green. It was tagged with the number 3. So when the receiving port received it, it said, oh, this is a broadcast for the green ones. So it sends that out to everybody plugged into its green ports. Okay, and it may be cascaded again to another one. This configuration, you see one on top of the other. You'll see this in the industry referred to as a stacked switch. Okay, multiple switches that are acting together. And sometimes, or particularly when I see the term stacked switch, that's actually multiple switches that act and appear as one. And we're going to see in the second session, we'll actually see where that comes into play with ZVM and the virtual switch. All right, so on a trunk port, I have a single cable carrying traffic for all of the LAN segments. But you see there, I excluded LAN segment number 6, the pink ones. That's not allowed because I configured the trunk ports. I configured as the network administrator. I say what VLANs, what LAN segments, what colors is this trunk port going to carry? And so I don't have to include everything, right? So I have a lot of control here. And switch administrators like to be able to exercise that kind of control. Now, we're going to come into some terminology problems, and I blame Z. So we're always, Z has been, traditionally we were the center of the universe, right? Everything we did, we could do no wrong. Well, when we started messing with the network, we actually made a mistake, and it's caused a lot of confusion, and that mistake has been around for about 25 years. When OSAs were first introduced, they introduced this idea of nobody worried about how device drivers talk to an OSA card. Then all of a sudden we exposed that information, so it created a problem. And the terminology is in the area we call layer 2 and layer 3. So when we're looking at a network, the OSI model for a network is a 7-layer model. Down at the bottom, layer 1, we're talking about how many volts are in what pins. How do we get data actually into a box, right? So I actually have some physical, there's physical parts of a network, but the data that flows around is a LAN segment, okay? In the case of Ethernet, we're talking about Ethernet frames, okay? If I have different kinds of network, FireWire networks, well, they have different frame format. But layer 2 says, appropriate to the media, here is the format. Here, layer 2, we're talking about frames. I don't know what's in them. It's just the mechanism for carrying data in a network. Okay, it doesn't care what's in it because it can carry all sorts of cool things. Okay, not just IP stuff, right? So at the layer 2, that is how 2 systems, the standard is defined for how 2 hosts, 2 network adapters more specifically, talk to each other, right? How do we format the data into a common language so that we all understand it? And this is where IEEE VLANs are implemented. The VLAN tags are in the layer 2 part of the network. They are in the Ethernet frame. At layer 2, as I said, we don't care about what kind of network we're using. Am I doing NetBIOS? Am I doing IP? Am I doing SNA? Am I doing AppleTalk? What exactly am I doing? There are a lot of different kinds of networks, but they all, when I'm talking about Ethernets, they would all have a layer 2 frame that all have the same format. The headers are all the same, right? Because I need to be able to segregate all those different kinds of networks, right? Now, In a physical switch, there's information in those headers that the switches use to learn. They look and they learn. That's one of the reasons you pay a lot of money for them. Because I do not want my network adapter being annoyed or being, I don't want to hear the conversations going on that my neighbors are having, right? I don't like it at home, and I don't like it, I don't want to listen to the people across the hallway at work having their doors open and me listening to their phone conversations. It's very distracting, right? And network adapters don't like it either, right? So to make the network more efficient, the switches actually they have what's called a forwarding database, and they learn. You can turn all that off, in which case, why did you pay all that money for it? But when you first plug in an adapter into a switch, it starts to learn about, well, who is that at the other end? It listens. And so it actually figures out what MAC addresses, what are the network adapters. We'll talk more about that. But it learns out who's there, and it filters traffic so that only traffic for that network adapter sits on that port. All right? So that's at the layer 2 level. Now, at layer 3, we have all the functions of layer 2 below us, but we also introduced the concept of a network. So the actual network makes its first appearance at layer 3. IP is a layer 3 protocol. Okay, SNA is layer 3. Underneath, everything below that, layer 1 and layer 2, I couldn't care less what kind of network it is. But at layer 3, that's where routers live. Parts of the network that understand, well, what is the network? What are subnets? How do I reach them? Where are the gateways? All of that stuff is a layer 3 protocol. And this is how we enable wide area networks. So a local area network is something that's just station to station on the same physical switch. There is an exception to that, but I'm not going to worry about that here. But in general, it's the same physical switch. When we think about, at the layer 3 switch, all of a sudden my network can now move across the world. So that's where I actually take a collection of LAN segments, hook them together, coordinate between them, and provide gateways or routers that get me from one to another, right? So network addressing is implemented in those gateways, in those routers, and that's where at the layer 3, that's where addresses come into play. Now I look at a physical switch. If I look at the exploded view, it kind of looks like this. Physical switch has all these ports in it, but internally the management software is associating each of those ports with a particular VLAN. Now, the other reason you pay a lot of money for these is because there's special circuitry in there. There's a grid in there, a fabric, a mesh, however you want to view it, that very quickly can move data from one port to another, okay? And there are internal ports in there that don't have physical, they're not plugged in anything, there's no place to see them. But they're all part of the fabric management, and they reach the internal gateway software that it listens to. So that thing in the middle is the international symbol for a router. So it's responsible for taking traffic and moving it around. That's where the firewall lives. It lives inside there. All right. There are some functions of a firewall that kind of reach out, and they're not layer 3 firewalls. They're actually layer 2 firewalls. So they sit out a little bit further. So you think of a firewall as actually, there's a ring, a set of concentric rings. And so there's a layer 2 firewall, and within that, there's a layer 3 firewall. And actually, you can get into, you don't see layer 4 firewalls, but layer 5 firewalls, we have those. So we look at this and we say, I have to, as the switch manager, I have to worry about all this stuff. And we see at the bottom, there's a trunk port, and it's actually connected to all of those, can be connected to all of those. So it's part of them, it participates with them, but it uses a slightly different set of rules for moving data to and from. All right, so that VLAN. So the VLANs come up into the IEEE world, and the VLAN's an IEEE standard 802.1q. .1q is important. I'll talk about that in a little bit, because there's more than one way to move data through trunk ports. But the IEEE 802.1q standard is just that. It's a standard. I can take switches from different vendors, tell it to use 802.1q on those trunk ports, and they will be able to talk to each other. If I don't do that, they're probably going to use proprietary protocol, which will only work with other switches from the same vendor. All right. So the standard says that each VLAN has an associated VLAN ID or VID. We say those are VLAN tagged frames because there's actually a tag in them. I'll show you what it looks like. They're allowed only on trunk ports. There is a trivial case where it is allowed on what we call an access port. So an access port is the one that's not sending VLAN tags. Normally, servers plug into access ports. That's a good thing. They don't care what VLAN they're on. They don't want them to have to worry about it. Now, an untagged frame can enter a switch. Okay, untagged frames are actually used in a switch, and it's how when the switch wants to communicate with a neighboring switch, it uses what's called the native VLAN ID. And it's sort of native, I know it's a dumb word in this context, but native VLAN ID is the VLAN which is associated with that we will use to communicate management data between the switches. Okay, is the way we keep servers from injecting data into the management infrastructure. How do you keep the management infrastructure of switches secure? Well, don't let other servers communicate on it. All right. So we take some special precautions there that you will see. Now, VLAN-aware bridges create those groups of end stations. So you saw those green ones we were looking at, the red ones. And so they're all grouped together in what looks like, it looks to you like there's one LAN segment. There's just a green thing, right? And I don't care that the servers are plugged into different physical switches. I don't want to care, because if I cared, I'd have to do something different, and I don't want to do something different. Right. Now, traffic between the VLANs is restricted, so you cannot get from one VLAN to another by doing what's called VLAN hopping. You have to go through a router, because for one thing, if you're plugged into an access port and you try to put a VLAN tag in there, I'm going to look at your frame and go, huh, I wonder what that is, and then throw your frame away saying, I don't know, it's a not valid format. And we actually use that discard of the frame to do diagnostics. Tell you when you have things configured poorly. Now we move up a level to layer 3. Now I want to talk about, this is layer 3 at the OSA level. Now this is where the confusion begins. So we've talked about layer 2, layer 3, very nice, love it. It fits with what I learned at school. It's, yeah, understand the network stack. And then IBM came along and said, let me talk about my layer 3 OSAs. And I'm like, wow, we talk too much. And so what it is, we talk about IP mode of our virtual switch, or it used to be called layer 3. We still see all over the place. You'll still see references. Does your vSwitch operating in layer 3 mode? This confuses network people, okay? Because when somebody says layer 3 with respect to the vSwitch or respect to an OSA operating in layer 3 mode, what they're really describing is the device driver protocol used by the device driver to talk to the OSA. Because at the IP level, we have IP packets. At the layer 2 level, we have Ethernet frames. An Ethernet frame carries an IP packet. But in IP mode, the device driver doesn't care about the Ethernet frame. It lets the OSA build that itself. So what it does is it sends IP packets. And so everybody says, oh, it's operating in layer 3 mode. No. It's a layer 3 switch. No, it is not. It is a layer 2 switch that is using, yeah, don't worry about what that protocol is. So we changed the names some time ago to call them IP mode and Ethernet mode for the virtual switch. And that really is just saying, does the vSwitch communicate with the OSA in IP mode, or does it communicate with the OSA in Ethernet mode? Does it send IP packets, or does it send Ethernet frames? Well, it depends, of course. And what it depends on what features of the virtual switch you're trying to use as to which one you're going to want. So the guest is doing this at the OSA level. OSAs accept IPv4 and IPv6. In the vSwitch level, we accept IPv4 only when operating in IP mode. So there's one of the, it depends. If your virtual machines want to use IPv6, they can't use IP mode vSwitches. They have to use Ethernet mode vSwitches. And in IP mode, the guest actually goes through a process by which it knowingly registers its IP addresses in the OSA or in the virtual NIC. So our virtual NICs simulate real ones. And so that way inbound packets can be routed by the OSA, by the vSwitch to the correct host, to the correct network adapter. Because I look in the packet, figure out what its destination IP address is, and send it to the guest that says, hey, I own that IP address. And if it get one and you go, huh, that's for an IP address that we don't recognize, then I need to send it to the virtual machine, which is defined to be the primary router. Virtual machines by default are non-routers. So I really don't want client networks set up to use router. We do not want routers running in virtual machines. They chew a tremendous amount of CPU, and they introduce an awful lot of latency in network traffic. But in this mode, the vSwitch, the OSAs are building the Ethernet frames around the IP packets. And all hosts that are using IP mode all have the same MAC address. If I went out and asked the physical switch, show me the MAC address of all these hundreds of virtual machines, they're all the same. Well, that's annoying. Actually, the physical switch doesn't care unless I wanted to use protocols that required uniqueness. Then all of a sudden I do care. So in layer 2, as I said, so this is where you need, if you want to use DHCP, you typically would use layer 2. DHCP is normally, as it's normally deployed, depends on the MAC address to uniquely identify a host. If everybody has the same MAC address, that isn't going to work, right? So in this case, the virtual NIC, the guest doesn't register a virtual IP address, it registers a MAC address instead. And the guest is responsible for building the Ethernet frames, and it's responsible for finding out the MAC address of the target. So it's really what I'll say, old school. But it might sound like old school, but this Ethernet mode is where we put most of our investment in the virtual switch. Okay. By the way, CP is watching. So just like a physical switch looks and learns, so does CP. Watches the traffic flowing and looks for guests trying to, when somebody says, what's your IP address? And they tell it, we look for that. CP looks and says, oh, he just identified himself. What's his IP address? That way it shows up in query vSwitch. Very handy thing to find out, because physical switches let me find that out also. I said I promised to tell you what a VLAN tag is. And very cleverly, it's sitting in the Ethernet header of an Ethernet frame. And what's kind of cool about this, if you are VLAN unaware, if you don't understand what a VLAN tag looks like, to you, it's gibberish. You look at it and go, I'm expecting to see, after the source MAC address, I'm expecting to see 0800. Instead, I see 8100. What the heck is that? Throw it away. I don't recognize it. But if I'm VLAN aware, then that means I do understand. I will understand if I see 8100. I know that the thing that follows it is the VLAN tag. And then after that is the 0800. Okay. So we expect to see tagged frames on a trunk port only. Access frames will typically discard them, right? And if I send one and it gets discarded, it's like, well, why am I sending an Ethernet tagged frame? I'm plugged into an access port. Well, something is wrong. I've done something wrong. Okay. We talked about the native VLAN ID, but in a virtual switch, the way we want to deal with this is I want you to code a virtual switch with native none. Native none tells CP if somebody on a virtual trunk port tries to send an untagged frame, discard it. I do not want virtual machines at any time interfering in any way whatsoever with the operation of the physical switch. If I don't have native none, then a mistake on my part could subject the network to risk. Okay, somebody's playing around and they do something which messes up the the spanning tree protocol. There's all sorts of things going on inside a switch. If they mess that up, then my network is going to shut down, and I'm going to make people mad. Right? Those when I tell you have VLAN aware, VLAN unaware. So when I'm VLAN unaware, I don't even see it. I don't even see in color. I don't even know it's blue, because I can't see other colors. If you don't know what the other colors are, how do you know that this one is blue? So all I know as far as my world is blue. If I want to get to someplace else, I have to go through a router to do it. But everybody I can talk to directly, we're all blue. So my guests are all connected to the virtual switch with virtual QDIO adapters, virtual NICs. And then that bridge is created between the virtual switch and the physical switch. Okay. So everybody who's in my same LAN segment, whether they're on the virtual switch or the physical switch, we're all part of one LAN segment, and we all talk directly to each other. Okay, which means we're all in the same subnet, which means we all have to have the same subnet mask. Okay, and if I don't, bad things happen. Now, what we want to do is the idea, somebody says, well, I want to create a separate virtual switch per LAN segment. I don't want to mess with this whole thing. I want red ones, I want green ones, and I want blue ones. I want to have red ports. Oh, by the way, that's 2 red ports because we need at least 2 OSA ports, physical OSA ports for redundancy. We don't do anything by ones. We do them by 2s. Okay. So for redundancy, I need 2 red ports. I need 2 green ones. and I need 2 blue ones. An OSA card costs anywhere between $14,000 and $18,000 US. Oops, no, I don't need that many ports after all. Okay, so sometimes network people tell me, no, we're going to do this. I tell them how much it costs. I tell their boss how much it costs. All of a sudden, people say, oh, we're not going to do it this way. Okay, instead, we're going to do it this way. Now, the idea says that I'm going to combine all of that traffic onto one virtual switch, which allows me to use one pair of ports, one pair of trunk ports, and handle all that traffic. But the reality of the situation is that very rarely, so networks has security policies as well as hosts. And typically one of the rules is internet traffic and intranet traffic shall not share the same infrastructure. Why? Because it's too easy. Humans make mistakes and bad things happen to good people. You just made a stupid error and now you've got internet traffic running around inside your intranet. Bad, right? So this is a case where I might have 4 OSA ports. I'll have 2 OSA ports handling the red traffic and 2 OSA ports handling the green and the blue traffic. Okay, so internet traffic on one, intranet traffic on the other. And this is perfectly okay. Those might even be in separate LPARs. The red one might be in a different LPAR from the green and the blue one. Okay. Oftentimes, the red one won't even be on Z. Okay. Often, there's a server farm which operates in the red zone. And you just won't have any of this red stuff on Z at all. It'll just mostly be blue and green, right? Perfectly okay with that. I'm not here to argue with clients. I don't argue with clients about what traffic do they want to put on the mainframe, right? Try to look for things you really shouldn't put on a mainframe, like routers. Okay, don't put them on there. That I'll argue with them about. But this, no, not arguing. It's a good balanced investment. Now, a VLAN-aware vSwitch sees all authorized LAN segments. So in this case, guests can belong to different LAN segments, different VLANs. And for all the ones that are authorized on my trunk port, I can share, I can communicate with all of those. And the virtual switch is responsible for all of the VLAN tags. It puts the tags on when stuff goes out through the trunk port. It takes the tags off when it goes into the guest. When the guest sends something, the virtual switch adds a tag and sends it out to the OSA. Unless it's going to a neighboring guest of the same color, in which case he doesn't bother doing that, right? You'll just send it to him. So this is a case of the trunk port sees multiple colors. Okay, continuing on. So let's look at our virtual NICs. And so they plug into our virtual switch, and our virtual NICs plug into either access ports or trunk ports and virtual trunk ports. And typically, you're going to plug a guest virtual NIC. They're going to plug into a virtual access port. I do not want the guests being VLAN aware. It is a waste of cycles for them. There's very few cases, in fact, I can't even think of any anymore, where I want the guest to be able to handle more than one VLAN on the same virtual network adapter. Okay? It's a one-off, and we don't like one-offs. It used to be done when we were doing those virtual firewalls. Okay? We don't do that anymore, so you don't really need that. I'm going to plug my virtual NIC into a virtual access port, which is the default unless you change it. What about that? But I got to know what virtual switch, what VLANs, what MAC address is it going to have? Is it an authorized to be a sniffer? Okay, I'm going to have to worry about that. And one of the first things I need to worry about is the MAC address. So a MAC address, and we call them virtual MAC addresses, but they're actually real MAC addresses. They appear on the physical network. And it's broken into 2 parts. It's a 6-byte value. The top high order 3 bytes are what we call the MAC prefix. It comes from system config. It'll be of the form 02 followed by 4 hex digits. The 02 is a shorthand. Technically, it doesn't have to be 02, but we enforce it that way. It indicates, it's a IEEE standard that indicates that the MAC address is not a burned-in MAC address. It's not globally unique. It's what they call a locally administered address, or an LAA. It's called a locally defined address. CP invented it, or the system administrator told CP what the MAC address is going to be. The point is that it came from VM. And all of a sudden, it's my responsibility to make sure I don't have 2 guests with the same MAC address. That would be bad. Okay? So I have more responsibilities when I have to manage a virtual MAC address. If CP is taking care of it, then it's not an issue. But if I have to manage it, I'm going to have problems. because I'm a human and I make errors. So there's a high order MAC prefix and low order MAC ID. These are the ones that you really have more control over. I can assign them specifically to a guest. I can predefine it, the NICDEF in the directory entry, or CP can assign it dynamically. Do I want a static value or persistent value, or do I want a dynamic value? I don't know. Is the guest using DHCP? Well, servers typically, when they use DHCP and they like to use it, they use something called persistent DHCP, which means they need the same MAC address every time. So I do have the capability of assigning it that way. Now, when I plug into a vSwitch, I got to think about, well, what are the vSwitch attributes? So we talk about is it operating in IP mode or Ethernet mode. We prefer to operate them in Ethernet mode, more functionality. A little more trouble for me as an admin, but I like it. I have to worry about an uplink port. How does it get in and out to the physical network? And there's something called a VSwitch Controller. But unless we otherwise configure it, the general architecture for Z is to keep the traffic as close to the virtual NICs as possible. So we keep it within the vSwitch. We go directly virtual NIC to virtual NIC. We don't go out over the wire. But if we have to go try to go out over the wire, we'll go to the OSAs. The OSAs will try to stay within the OSA. Is it going to an LPAR? Am I sharing this OSA with another LPAR, and is the destination something that the OSA knows is in the next LPAR? If it is, it'll short circuit it unless it's been told not to. Okay, but if it's not known to the OSA, not known to the vSwitch, then it's going to go out to the physical switch. Okay, and the physical switch looks at the destination and says, what do I do with it? Well, now he's just following standard switch rules for what to do with it. Is it somebody I know? No. Well, if it's nobody he knows, he just throws it away. He doesn't tell anybody either. He says, I couldn't deliver it, I threw it away. Not my problem. Because it's at the layer 2. There is no, I don't care about routers. Because you didn't send it to a router, you sent it to a specific MAC address, and I don't know who that is, so they're not getting it. Okay? Now, the vSwitch controller is responsible for OSA housekeeping. They actually take care of a lot of housekeeping on behalf of CP. They are a specialized TCP IP stack. They're responsible for starting, stopping, monitoring, querying the OSA. They are not involved in data transfer. So it says, oh, it's a TCP IP stack. Yes and no. We use it because the device driver that's in there didn't want to have to write it again. But from a security perspective, the controllers are not involved in data transfer. The system comes with 4 of them. Unless somebody tells you to create one, and the somebody would be the support center, because they want to do something special and they don't want to interfere with what else is going on in your system. They want to create another vSwitch that you can use because they need to run some diagnostics of some sort. But I tell the clients, don't create more of these. We ship 4 of them. That's all you need. Keep them logged on. If something gets logged off, log it back on again. If it keeps logging off, something is wrong. Go look. Right? Because if it logs off, CP will automatically fail over to another one, which is why we want to have more of them logged on. Okay? And in fact, we want all 4 of them there. If they have a problem with the OSA, they will issue messages to their own virtual consoles, and they will issue messages to the operator. Yes, the messages to the operator are quite informative. The ones on the vSwitch controller console are the ones you might actually use to solve the problem. They have more information about what the problem is. And typically, in fact, you'll see that we got a PMR open, case open. Then what we do is we ask for, do you have the controller? We want the operator's console, and we want a copy of the controller console. Okay, we almost don't care what's in the operator's console because it'll be duplicated in the virtual machine console itself, right? So it's important for diagnostics. The uplink port in the vSwitch is responsible for getting data from the network into the vSwitch and for getting data outbound, okay? So if the vSwitch doesn't recognize the destination, it's going to send it out to the uplink port. Now, if there's no uplink, data can only move among the guests, okay? That's fine. If you're wanting to test second-level systems, if you don't want really give it access to the physical network, you can use a virtual switch without an uplink port, okay? And when it operates that way, it operates like what we call a guest LAN, a more primitive version of the vSwitch, but it's got better security controls. I don't like guest LANs. I do like virtual switches. So we like to use them even without an uplink. But of course, without an uplink, nothing's moving to or from the network, right? Now, one of the things that the uplink can do is we have, if for high availability, you want more than one, okay? If the physical port fails, if the OSA fails, if the cable comes unplugged, we want to be able to switch over to another Ethernet port, right? We can operate them individually, 2 or 3 of these. in failover mode. If this one fails, go to the next one. If that one fails, go to the next one. If that one fails, cycle back around to the first one again. If they're all dead, just sit there and wait for one of them to come active and then start using it. Or we can operate in link aggregation mode. I'll talk about that in the second presentation. That's available for link aggregation as Ethernet mode only. So one of the places we start our configuration exercise is in the system config file. And there's a VLAN statement, and it has something for best practices there. There are two particular values, these 5 values that are of interest. But what I want to do is, first of all, set limit transient 0. The default is infinite, blah, 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 technical stuff. The point is that if I set it to 0, virtual machines, class G virtual machines cannot create guest LANs. Okay? A class G virtual machine with the default configuration can create its own guest LAN. It can also invite its friends to connect to it. Nothing will stop them. This is why we don't like guest LANs. They're not secure enough. Okay, I can't stop class G virtual machines from connecting to them without getting rid of the couple command. I don't want to get rid of the couple command because I need the couple command to connect to a vSwitch. Right, so and I don't want to get rid of the define command because define LAN command because, well, I get rid of define, and there are lots of other things I want to define besides this. So the simple case is to put limit transient 0 in the VLAN statement system config. The other thing that I suggest to clients is MAC protect on. The default is off. I would have preferred that the default had been on. Okay, security by default. And so every virtual switch inherits its MAC protect setting from this one. But you can override it at the vSwitch level. And then the virtual NICs carry the attribute. They have this attribute also, and their default comes from the virtual switch that they're connecting to. The administrator can override that at the virtual NIC level as well, right? So we like to have MAC protect on as the default. And if you want to change it for a particular purpose, you can, but you do that at a lower level. I don't want to turn it off for everybody. So normally, a virtual machine has no reason to be registering a MAC address other than the one that was assigned to it. There are some special protocols that require it, and for those virtual machines, I'll turn MAC protect off, but only on the virtual NIC that needs it, right? And then I have MAC prefix and user prefix. So MAC prefix, it sets that the MAC prefix for the CP-generated MAC addresses. Every instance of CP needs to have a different MAC prefix. This is how I avoid duplicate MAC addresses in my network. The same way I deploy a new ZVM instance, I give it a new node name, a new system ID, give it a new MAC prefix. It needs to be one of the things that you assign when you deploy. Every CP instance needs a MAC prefix that's unique from all the others. And in fact, if this system is part of an SSI cluster, when it tries to join, CP will check, and it will check with all the other members, and this one will be rejected, will not be allowed to join the cluster if it has a MAC prefix that duplicates one of the other cluster members. Okay. Now the user prefix is different. The user prefix is what prefix to use when you set the MAC address. Okay. If you've got the MAC ID value in the NIC def, the MAC prefix that will be used will be this user prefix value. Now it defaults to the MAC prefix value. Okay. Now that isn't going to work in an SSI cluster because in an SSI cluster, the user prefix, the same way MAC prefix must be different. User prefix must be the same in everybody who's sharing the directory. Okay. Now that is enforced in a single system image. If I've got non-SSI images that are sharing a directory, that MAC ID will be used on multiple LPARs. Well, then they better have different MAC prefixes. And so I want if I'm in an SSI cluster, MAC prefix has to be different, user prefix has to be the same. Okay? Do not allow either of those to default to 020000. That's the default. One thing, you have to re-IPL if you want to change it. Number two, that's an indication to me that you weren't reading. Okay, you didn't follow instructions because you didn't come to my class because I told you that you needed to set the values and you didn't. So it's how I detect the presence of a VML par which might be incorrectly configured. Somebody configured it halfway and stopped. Because if they have one of these, it says 020000, why don't they have more than one? Okay, so never let it default to that value. And if you want to create a virtual switch, then you will in system config or by CP command, you use the define vSwitch command, right? You really just need define vSwitch, give it a name, say Ethernet, tell it what OSA devices it's going to use, or is it part of a link aggregation group, in which case I'll specify the group name. Is it VLAN-aware or VLAN-unaware? Default is unaware. The default is also native 1, not native none. I don't like that default because it can unintentionally open up the physical switch to damage. So best practice, VLAN-aware, native none. If you're going to plug an OSA, those OSAs, into a trunk port, you should code VLAN-aware, native none. That means there are no default VLAN IDs. You have to assign them at the virtual NIC level. Okay. There are other options on here. I typically recommend, and actually even that port-based, you don't even really need to worry about that. But these are the ones typically going to use. If you're tempted to use the other ones, I say, let's talk before you use any of the other options. In general, I suggest not creating IP mode vSwitches. Okay. Again, they restrict you down the line, and you're just deferring the idea, I'm going to have to manage MAC addresses. Might as well just start from the beginning, and then you've got all the capabilities. All of our investments in the virtual switch have been in Ethernet mode. So you want to take advantage of those. It's easy if you're already in Ethernet mode. Okay? You don't have to, upend your processes. All right, so the OSA devices, default is RDEV none, which says that you're not going to have any uplink at all. Excellent for second level systems. I can specify the device numbers. And so those will be in triplets. So there'll be a sequence of 3 devices. I specify the first device of a triplet. I can optionally specify a port number. The default will be port 0. Obviously, that port number applies only to OSA cards that have multiple ports on a single chiplet, right? For the ones that have just one port on the chiplet, it'll always be port 0. I mentioned before that they're round robin failover. You can do a set vSwitch switchover command if you want to change it on the fly. Right? Or you can specify a group and a name, and that will be for link aggregation or channel bonding, and again, available Ethernet mode only. Now the virtual NIC, that's the NIC def, goes in the directory. And there I'm going to specify, again, the first of a triplet. When I do a NIC def, it'll define 3 devices. In this example, NIC def 1100, it'll create 1100, 1101, and 1102 automatically. I don't have to worry about the other devices. So I can specify what vSwitch it's going to connect to, what the MAC ID is. Okay, I can put that here, persistent assignments. I have, for one of my clients, I created an exit in Dermate so that as they deploy NIC defs, it automatically assigns a MAC ID because they wanted persistent MAC IDs. They don't want being different every time because they have diagnostic tools and mapping tools and all sorts of stuff that let them, given a MAC address, they can immediately know by looking in their tools, by doing a lookup, is figuring out what virtual NIC has that. If you know what virtual NIC, that is to say, what virtual machine owns that MAC address. They can look that up very quickly. Okay, so they assign the MAC IDs in there. If you don't assign it, CP will. All right, and I can say, is this a virtual access port or virtual trunk port? And by the way, some people back on the define vSwitch command like to put there, one of the options you can put here is port type access or port type trunk. Do not code it. It does not describe the OSA connection. It describes the default virtual NIC connection, okay? We should never have put it in there. Creates too much confusion. So I tell people don't code it. If you have a reason to be specifying the port type, you want it to default to trunk. So don't put port type if you want it to default to access. Do not put port type trunk on the vSwitch, or what happens is you start creating really weird virtual machine configurations to get it to work. And then it works by accident, not by design. Okay? You can still make it all work, but it involves native VLAN IDs, and it's just a mess. So you want virtual machines having port type access. And then if I'm going to allow it to be a sniffer, I authorize that here as well. By the way, no promiscuous is the default for our virtual NICs, and port type access is the default. And those are defaults we want to keep. So it's important for a security point. So it's kind of like a security thing, right? So we don't want virtual NICs sniffing other traffic unless I tell it. But that is a nice way. If you want to be able to put the virtual NIC in sniffer mode, you can collect an Ethernet trace and download that to Wireshark and look at it that way. What we really want to do, there's a set vSwitch grant command, and we want to try to eliminate its use. A long time ago, we shipped some support for the vSwitch, which allowed CP to handle all the configuration, and I don't need to issue the set vSwitch grant command. because I can put the VLAN ID directly on the NIC def. I didn't used to be able to do that. So I had to use the grant command to accomplish it. So now I don't need to do that. And it also means I don't need to hunt for where do you do your grant commands? Do you do them in Autolog 1? Do you do them in Autolog 2? Do you do them somewhere else completely separate? Do you do them in system config? And I go, we don't care. It's in the directory, right? Finding the vSwitch, this is just vSwitch with the Ethernet option. In this case, you can use port-based. Port-based is slowly becoming the default. Everything will be port-based in the future. We allow a RACF or the ESM to control vSwitch access. This was really good before we had the ability to put the VLAN ID in the directory. Now that we have the VLAN ID in the directory, the need for this is less important. And in fact, I recommend to my clients not to do it unless they need it for audit purposes. So we really aren't interested anymore. I'm not as interested as I used to be in managing the vSwitch with the external security manager. But if it's needed for audit purposes, you may still want to go with this. And if I find myself in a multi-tenant situation, I may want to come back to it. Talked about promiscuous. There is something called a QDIO port isolation or QDIO connection isolation, as ZOS knows it. What it shuts off is the ability for guests to talk to each other at all. This has really been replaced by something called VEPA, Virtual Ethernet Port Aggregator support in the vSwitch. Because if I turn this on, what's going to happen is it shuts off all the short circuits and the data is going out to the network. And we invented this before we had VEPA. And it really is designed for a case that traffic can't come back. Okay, we don't want that traffic coming back, but it prevents guests from talking to each other. If we're going to do that, we have actually better ways. This is very heavy-handed. This is Thor's hammer, and we don't need to use it here. We can use VEPA mode and have a more fine-grained control over that kind of traffic decision. So best practices for all vSwitches. To summarize, I prefer that you use Ethernet mode. Do not specify port type trunk on the defined vSwitch. Do not specify the controller option. Allow it to default. There is a function in the TCP/IP configuration that says controller on. Yeah, don't put that in your own IP stack. You do not want your IP stack becoming a controller for the virtual switch. Because if the controllers go down, by the way, if no controller is available, the uplink will stop. We're not going to allow using the uplink if we can't control it. If we can't see what's happening. Without the controller, CP has no idea about the status of the NIC. Okay? Doesn't know if there's been any errors raised or anything like that. So the uplink will stop. Specify MAC protect on, limit transient 0 on the VLAN statement in system config. Use the NIC def to assign your VLANs. Define the vSwitch with VLAN-aware native none. That way a guest that has not been given access, it'll get errors. If you don't assign it a VLAN ID, it won't be able to connect. Okay? And you also have no chance of untagged frames escaping out of ZVM. And here I say use ESMs and groups. If you're using an ESM, use groups to manage your VLAN assignments. Simplifies a lot of changes. Now, in a couple of weeks, I'll be talking to you about more advanced functions. We'll talk about link aggregation, how to share a virtual switch among multiple LPARs. We'll talk about our hypersocket bridge capability, the VEPA support I just mentioned. Talk about that, how to configure that, what it really means. Talk about monitoring through SNMP, and perhaps more importantly, the thing I use most often out of this presentation actually is my chart on diagnostics. I'll talk to you about that in a couple of weeks. And just to illustrate, so vSwitch, one of the important investment areas in ZVM, so I'm very happy to have been associated with it all these years. And the team does a great job at providing functionality, working with clients, using Agile, and actually talking with the clients about what they need, letting them see a prototype, giving feedback. So it's been a very successful collaboration with clients. But a lot of stuff. Investment isn't what it used to be, of course, smaller organization, but still it is a priority for ZVM to have that. If you want to kind of get started, you're getting started in networking. So for that, YouTube is probably best if you're getting started in networking. But the ZVM connectivity book does have pictures and does define the various kinds of virtual networking capabilities that we have. I appreciate your attention this morning, and thank you for your time, and enjoy the rest of your day. Enjoy the rest of your afternoon. Back to you, Bill.
All right. Thank you very much, Alan. Thanks, everybody. Have a great week, and we'll talk to you next Monday.
Thanks for watching. If you enjoyed this video, don't forget to like and subscribe to see more videos like this one. Have a suggestion for another video topic? Feel free to leave a comment below.